Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of person who finds peace in the slow drift of water and the mysteries hidden beneath ancient waves. Either way, tonight's journey is for you. You have nothing to do but rest. Let your mind grow still like the surface of a calm ocean, your breathing slow like gentle tides, and your body relax as if you're floating effortlessly in warm primordial waters. Because tonight we aren't simply thinking about the sea. We're drifting back through time itself, to oceans that existed long before humans, before dinosaurs, before even the shape of the continents we know today. We'll explore seas so ancient, they witnessed the very first complex life emerging from simple cells. Waters so warm and welcoming they cradled creatures that have no modern equivalent. Oceans so vast they wrapped around a single supercontinent like a liquid embrace spanning the entire planet. These aren't just any waters. These are the seas that shaped our world, that carved the landscapes, that gave birth to the oxygen we breathe and the life that fills every corner of Earth today. And in their depths, their warmth, their slow and patient movements, there is something deeply calming. Something that reminds us that change happens slowly, that vast forces work with quiet persistence, that the world has always been in gentle transformation. Tonight you'll hear about Panthalassa, the superocean that held 70% of Earth in its liquid grasp. You'll learn of the Cambrian seas where life first learned to see, to hunt, to glow in the darkness. You'll discover the Tethys Ocean, a tropical paradise that once stretched from the Caribbean to the Himalayas. You'll float through the warmest waters Earth has ever known, where even the poles were as warm as a pleasant summer day, where no ice existed anywhere on the planet for millions upon millions of years. Some of what you hear tonight might surprise you. You might find yourself curious about these lost worlds, these vanished ecosystems, these creatures that once filled waters now gone. But that curiosity will be gentle, like wandering about a dream as you drift towards sleep. Let it wash over you softly. Let the words become like waves, rhythmic and soothing, carrying you deeper into rest with each passing moment. And just before we begin, if these calm explorations of ancient waters help you unwind, if they give you a quiet way to end your day, consider subscribing to Deep Sleep Seas. It helps others find their way here too, one peaceful soul at a time, all seeking the same gentle rest that comes from drifting through time and tide. Now close your eyes if you haven't already. Take a deep breath, and let's slip beneath the surface of time itself, into waters that have long since evaporated, transformed, become the stone beneath mountains and the salt in modern seas. Let's visit the ancient oceans that once were, and in their memory find the deepest, most peaceful sleep. In the very beginning, Earth had no oceans at all. 4.5 billion years ago, our planet was a molten sphere too hot for liquid water to exist anywhere on its surface. The entire world glowed red and orange with heat, a sphere of churning rock and metal floating in the darkness of space. Everything was fire and violence, bombardment and chaos. Water, if it existed at all, was locked away in the rocks themselves or hidden in the icy comets that occasionally struck the young planet's surface. But slowly, so slowly you couldn't perceive it, even if you watched for 1,000 human lifetimes, Earth began to cool. The surface hardened into a thin crust. Steam rose in impossible quantities from volcanic vents scattered across this newborn landscape. The atmosphere grew thick and heavy with water vapor, carbon dioxide, and gases we would find toxic today. For millions of years, the sky itself was an ocean of moisture waiting to fall. And then, somewhere around 4 billion years ago, it did. Rain began. Not a gentle shower, not even a storm by modern standards, but a deluge that may have lasted for thousands of years without pause. Water poured from the sky in sheets, in torrents, in quantities difficult to imagine. It filled every depression, every valley, every low place on the cooling surface. It gathered and pooled and spread. Rivers formed in moments and vanished just as quickly as the landscape shifted and changed. Oceans began to accumulate in the deepest basins, growing larger with every passing century. These first oceans were not like the waters we know today. They were hot, perhaps as warm as 60 or even 70 degrees Celsius in places, far too hot for any life we're familiar with. They were acidic, filled with dissolved minerals and volcanic gases. They tasted of iron and sulfur and salt. The sky above them was not blue but a murky orange-brown, thick with clouds that blocked most of the sun's light. Lightning split the darkness constantly, thousands of strikes every moment across the entire globe, illuminating the strange and alien landscape below. But in that alien chemistry, in those hot and toxic waters, something miraculous was preparing to happen. The very conditions that would seem hostile to life were actually the perfect laboratory for its creation. Energy from lightning strikes, from volcanic heat, from the ultraviolet radiation pouring through the thin atmosphere, all worked together to create increasingly complex molecules. Amino acids formed, simple organic compounds accumulated along the shores and in shallow pools. The oceans became a kind of primordial soup, rich in the building blocks of life. For hundreds of millions of years, nothing moved in these waters except the currents and the tides. No eyes looked out from beneath the surface. No creature hunted or hid or sought a mate. The oceans were utterly silent except for the sound of waves against rock, the hiss of volcanic gases, the distant rumble of eruptions. But they were not empty. In countless tiny pockets, in chemical gradients along thermal vents, in the spaces between minerals on the ocean floor, chemistry was becoming biology. The first life was simple beyond imagination. Single cells, if you could even call them that. Perhaps just molecules that could make copies of themselves, not quite alive in any way we would recognize. But they persisted, they replicated, they began the slow process of evolution that would eventually lead to everything else. And all of this happened in water, in the ancient seas that covered most of the planet, in the gentle and patient medium that could dissolve nutrients, carry them long distances, protect fragile chemistry from harsh radiation, and maintain relatively stable temperatures despite the chaos of the surface world. By 3.5 billion years ago, life had definitely taken hold. Bacteria thrived in countless varieties, each adapted to different conditions, different temperatures, different chemical environments. Some found their energy in sunlight, beginning the slow process of photosynthesis that would eventually transform Earth's atmosphere. Others fed on chemicals released from volcanic vents, living in total darkness in the deepest parts of the ocean. These microorganisms were tough, resilient, patient. They spread across the seafloor and through the water column. They built structures called stromatolites, layered mounds of sediment and bacterial mats that still exist in a few places today, living fossils that connect us directly to Earth's earliest seas. The oceans themselves were slowly changing. As photosynthetic bacteria multiplied, they began releasing oxygen as a waste product. At first, this oxygen was immediately absorbed by dissolved iron in the water, creating rust that settled to the seafloor in distinctive red layers called banded iron formations. For hundreds of millions of years, the oceans served as a kind of rust factory, slowly purifying themselves as the iron precipitated out. Eventually, around 2.5 billion years ago, the oceans began to carry dissolved oxygen. The water chemistry shifted fundamentally. The stage was being set for more complex life, though that emergence was still more than 1 billion years away. These early oceans were patient. They had all the time in the world. They absorbed the sun's energy day after day, year after year, millennium after millennium. They cycled nutrients from the deep to the surface and back again. They eroded the continents slowly, grinding rock to sand and dissolving minerals to carry them across vast distances. They created environments and maintained them for eons. They held the entire history of early life in their depths, preserving it, protecting it, allowing it to slowly experiment with new forms and new ways of living. And through all of this, through billions of years of change, the fundamental nature of water remained constant. It was the perfect solvent, the perfect medium for life, the perfect buffer against extremes. It absorbed heat in summer and released it in winter, moderating temperatures across the entire planet. It evaporated from the surface and fell as rain on the land, creating rivers that flowed back to the sea in an endless cycle. It was transparent enough to allow light to penetrate, yet dense enough to support floating organisms. It expanded when it froze, protecting deeper waters from complete freezing even in the coldest conditions. Every property of water seemed almost designed to nurture and protect life, to give it time and space to develop and diversify. In these first oceans, in their warmth and their chemistry and their endless patience, the story of life on Earth began. Everything that followed, every creature that has ever swum or walked or flown, every ecosystem that has ever existed, all trace their ancestry back to those early seas. We are, in a very real sense, children of the ancient ocean, The salt in our blood echoes the composition of primordial seawater. The cells in our bodies still carry the machinery developed by bacteria in those first warm seas. When we float in water, when we feel its gentle support and calming embrace, we are reconnecting with something ancient, something that existed before continents had names, before mountains had been raised, before life had even learned to see. Around 300 million years ago, the world looked nothing like it does today. The continents had drifted together, colliding slowly over millions of years, merging into a single massive landmass. This supercontinent, called Pangaea, stretched from pole to pole, a vast C-shaped expanse of land dominating one side of the planet, and surrounding it, wrapping around it, covering everything that wasn't Pangaea, was a single enormous ocean. This was Panthalassa, a name that comes from ancient Greek words meaning all sea. And the name was appropriate, because Panthalassa truly was all the sea that existed, one global ocean, uninterrupted, stretching from one edge of the world to the other. Try to imagine it. An ocean so vast that at its widest point, near the equator, it spanned nearly twice the width of the modern Pacific Ocean. From the eastern shore of Pangaea, you could sail west and not see land again for thousands upon thousands of miles. The horizon would stretch endlessly in every direction, day after day, week after week, month after month. No islands would break the monotony. No distant mountains would appear on the skyline. Just water, deep blue water, extending to every horizon, reflecting the sky above, moving in slow, patient swells that had traveled unimpeded across half the planet. Panthalassa covered approximately 70% of Earth's surface during its peak. That's an almost incomprehensible amount of water. If you could somehow stand at the center of this ocean, you would be farther from any land than any point on Earth today. The nearest shore might be 2,000 miles away in every direction. You would be floating above ocean floor that had never seen sunlight, that had been dark for its entire existence, that might be 3 or 4 miles beneath your feet. The pressure down there would be crushing, the temperature near freezing, yet even in those depths, life would exist. Strange creatures adapted to the darkness, to the cold, to the eternal night of the abyss. But we're interested in the surface waters, in the gentle waves that rolled across Panthalassa under ancient skies. These were calm waters, for the most part, without the complex geography of multiple ocean basins, without the many continents and island chains that create complicated current patterns today. The circulation in Panthalassa was simpler, more straightforward. Great gyres formed, massive circular currents that moved water slowly from the equator toward the poles and back again. Near the equator, the water was warm, heated by the tropical sun that beat down day after day, year after year. The surface temperature might have reached 28 or even 30 degrees Celsius, warm as a pleasant bath, comfortable enough to float in indefinitely. These warm equatorial waters were home to abundant life. By this time in Earth's history, the oceans had been populated for hundreds of millions of years. Complex creatures had evolved, experimented with different body plans, diversified into countless species. Swimming through Panthalassa's sun-warmed surface, you might have encountered ancient relatives of modern fish, though many would look strange to our eyes. Sharks prowled these waters, already ancient by this time, their basic body plan proven effective over hundreds of millions of years of evolution. Cephalopods drifted in the currents, some with straight shells, others with coiled ones, ranging from tiny to enormous. The deep waters of Panthalassa held their own mysteries. In the absence of many shallow seas, much of the life in this superocean existed in the open water or on the deep sea floor. Trilobites, though past their peak of diversity by this time, still scuttled across the bottom in some regions. Strange armored fish explored the depths, simple corals and sponges clustered around seamounts and underwater peaks, creating small oases of life in the vastness of the abyss. One of the most remarkable things about Panthalassa was its relative stability. Without multiple ocean basins to complicate things, without narrow straits and channels to create turbulent flows, the water in this superocean moved slowly, predictably. The same currents flowed in the same patterns for millions of years. Creatures adapted to specific temperature ranges could find those conditions persisting generation after generation, allowing evolution to fine-tune adaptations over immense periods of time. Along the coast of Pangaea, the edge of Panthalassa lapped at shores that stretched for thousands of miles without major interruption. These coasts saw gentle waves most of the time, as the vast fetch of the ocean allowed swells to organize into long, regular patterns. Storms occurred, of course, but without the complex interactions of multiple ocean basins and varying depths. Even the largest storms in Panthalassa had a certain orderliness to them. They were powerful, yes, capable of generating enormous waves, but those waves traveled vast distances and gradually lost their energy spreading across so much water. In the subtropical regions, warm water from the equator mixed slowly with cooler water from higher latitudes. These mixing zones were particularly rich in nutrients, supporting blooms of plankton that in turn fed larger creatures. Flocks of ancient flying reptiles might have congregated here during certain seasons, diving into the water to catch fish that came to feed on the plankton blooms. The water itself would have sometimes taken on a milky or greenish tint from the sheer density of microscopic life. Near the poles, Panthalassa became much colder, though during much of the time that Pangaea existed, there was little or no ice even at the highest latitudes. The water there might have been only a few degrees above freezing, dark for much of the year in winter, bathed in continuous twilight during the brief summers. Few creatures ventured into these cold waters, but those that did found an abundance of food during the summer months when nutrients welled up from the deep and the long days allowed constant feeding. Panthalassa existed for hundreds of millions of years, though its exact configuration changed as Pangaea itself slowly evolved and eventually began to break apart. During all that time, this single global ocean shaped Earth's climate. It distributed heat from the equator toward the poles, moderating temperatures that might otherwise have been even more extreme. It absorbed carbon dioxide from the atmosphere, helping to regulate the planet's greenhouse effect. It provided a stable environment for evolution to work its slow magic, allowing countless experiments in form and function to play out over geological time. There's something deeply peaceful about imagining Panthalassa, one ocean, uninterrupted, covering most of the planet. The same water touching shores separated by thousands of miles, currents that flowed for eons, waves that traveled farther than any wave travels today. In its vastness and its simplicity, Panthalassa represents a kind of oceanic perfection, a time when the sea truly did cover the Earth, when water was the dominant feature of our planet, when anything that lived in the ocean could theoretically travel anywhere else in the ocean without crossing land or entering drastically different conditions. When Pangaea began to break apart, starting around 200 million years ago, Panthalassa began to change. New ocean basins formed as the continents split and drifted away from each other. The Atlantic Ocean was born, narrow at first, gradually widening over tens of millions of years. Panthalassa contracted, though slowly. Eventually, most of what had been Panthalassa became what we now call the Pacific Ocean. The Pacific is, in a sense, the direct descendant of that ancient superocean, the last remnant of a time when one body of water ruled the planet. When you look at the Pacific today, when you stand on its shore or sail across its still vast expanse, you're experiencing an echo of Panthalassa, a connection to that deep past when the ocean was even more dominant than it is now. If we drift back even further in time, past Pangaea and Panthalassa, past the age of fish and forests, we come to a period that paleontologists call the Cambrian. This was a time roughly 540 million years ago, and it marks one of the most important events in the history of life on Earth. The oceans during the Cambrian period witnessed what scientists call the Cambrian explosion, a relatively brief span of time, perhaps 20 or 30 million years, during which life diversified at an unprecedented rate. Suddenly, in geological terms, the seas filled with creatures more complex and varied than anything that had existed before. The Cambrian oceans were warm, much warmer than the seas we know today. There was no ice at the poles, no glaciers carving through mountains, no frozen seas anywhere on the planet. The entire Earth enjoyed what might be called a greenhouse climate, with high levels of carbon dioxide in the atmosphere trapping heat and keeping temperatures elevated everywhere. At the equator, sea surface temperatures might have reached 30 degrees Celsius or even higher. Even near the poles, the water would have been temperate, perhaps 15 to 20 degrees, warm enough for abundant life. These warm waters were shallow in many places. Sea levels were high during much of the Cambrian, and extensive shallow seas flooded low-lying portions of the continents, creating vast areas of warm, sunlit ocean that was rarely more than a few dozen meters deep. These shallow seas were like enormous bathtubs, heated by the sun, rich in minerals eroded from the land, perfect environments for life to experiment with new forms. An experiment it did. The Cambrian explosion gave rise to most of the major groups of animals we know today. Arthropods appeared, creatures with jointed legs and external skeletons, the ancestors of modern insects, crustaceans, and spiders. Mollusks diversified into many forms, some with shells for protection, others without. The first simple chordates emerged, distant ancestors of all vertebrates, including fish, reptiles, birds, mammals, and ultimately humans. Sponges and jellyfish, which had existed for some time, became more diverse and more abundant. But it was the trilobites that truly dominated the Cambrian seas. These arthropods, with their distinctive three-lobed bodies and compound eyes, evolved into thousands of species. They ranged in size from smaller than your fingernail to larger than a dinner plate, though most were somewhere in between. Some trilobites crawled along the seafloor, feeding on organic debris or hunting tiny creatures in the sediment. Others swam through the open water, chasing plankton or smaller prey. Some had elaborate spines and projections, possibly for defense or perhaps for some purpose we can only guess at. Others were smooth and streamlined, built for speed and agility. The Cambrian seas were also home to some truly bizarre creatures, animals so strange that when their fossils were first discovered, scientists struggled to understand what they were looking at. There was Anomalocaris, a predator that could grow up to 3 feet long, enormous by Cambrian standards. It had a circular mouth lined with sharp plates, 2 large grasping appendages for catching prey, and compound eyes that may have been the most sophisticated vision system in the ocean at that time. Anomalocaris was likely the apex predator of its ecosystem, though it probably fed mostly on smaller prey, and may have been more of a gentle filter feeder than a fierce hunter, despite its fearsome appearance. Then there was Hallucigenia, a creature so odd that scientists initially reconstructed it upside down and backward. It was a worm-like animal, covered in pairs of stiff spines on its back and pairs of legs underneath, though the legs and spines looked so similar that for years researchers weren't sure which was which. Its name reflects the surreal, dreamlike quality of its appearance. It seemed to defy easy classification, a reminder that evolution in the Cambrian was still experimenting freely, trying out body plans that sometimes worked and sometimes didn't. The ancient worm Otoia prolifica lived in self-constructed burrows, shaped like the letter U beneath the seafloor. It would hide in these tubes and ambush prey that passed overhead, striking upward to grab creatures with its proboscis and pulling them down into the sediment to consume. Fossilized Otoia have been found with the remains of their last meals still visible inside their bodies, providing direct evidence of predation and, in some cases, cannibalism in these ancient seas. The seafloor of the Cambrian oceans would have looked alien to our eyes, yet also strangely familiar. Fields of small, hard-shelled creatures covered the bottom in places, like a carpet of shells in varying shapes and sizes. Sponges grew in clusters, filtering tiny particles of food from the water. Burrowing animals created complex tunnel systems in the sediment, mixing and aerating the mud, where rock outcrops rose from the seafloor. Creatures clung to every available surface, filtering food from the currents or hunting smaller organisms in the crevices. In the water column above, a snow of organic particles drifted constantly downward, the remains of dead organisms and fecal pellets from the creatures living in the sunlit surface waters. This marine snow provided food for bottom-dwelling creatures and helped to transport nutrients from the surface to the deep. The currents that swept through these Cambrian seas were gentle most of the time, allowing this organic matter to settle gradually rather than being swept away to distant parts of the ocean. The water itself would have been clear in most places, though perhaps with a slightly different tint than modern seawater due to differences in chemistry. The Cambrian atmosphere contained less oxygen than today's, which meant the water also carried less dissolved oxygen. This limited the size that animals could grow to, since larger animals need more oxygen to power their metabolism. But within these constraints, life flourished in astonishing variety. One of the most significant developments of the Cambrian was the evolution of vision. Early animals had been essentially blind, detecting the world through touch and chemical signals. But during the Cambrian explosion, eyes appeared in multiple lineages independently. Trilobites developed compound eyes with hundreds or even thousands of individual lenses, each made of calcite, a transparent form of calcium carbonate. These eyes could detect motion and form images, giving trilobites a huge advantage in finding food and avoiding predators. The evolution of vision may have driven an evolutionary arms race, with predators becoming better at seeing prey and prey developing better ways to hide or escape. The shores of Cambrian seas lapped against landscapes that would look barren to us. There were no forests, no grasses, no flowering plants. The land was essentially bare rock and sand, perhaps with a coating of bacterial mats or simple lichens in some areas, but otherwise lifeless. All the action, all the drama of life and death, reproduction and evolution played out entirely in the water. The sea was everything, the only place where complex life existed, the only environment where the story of Earth's biology was being written. As the sun set over these ancient waters, the surface would have glowed sometimes with the soft light of bioluminescence. Though we'll explore this in more detail later. It's worth noting here that some of the earliest forms of biological light production may have appeared in the Cambrian seas, as creatures began to experiment with the chemistry of making their own light. The glow would have been faint, visible mostly in the deeper waters where sunlight couldn't reach, but it added another layer of complexity to these emerging ecosystems. The Cambrian period lasted for more than 50 million years, from about 540 million years ago to 485 million years ago. During that entire span, the seas were home to constant innovation and experimentation. Many of the creatures that appeared during this time left no descendants. They were evolutionary experiments that ultimately failed, wiped out by competition, predation, or changes in the environment. But others founded lineages that persist to this day, their basic body plans proving so successful that they've been maintained, with variations, for 500 million years. When we look at the fossil record from the Cambrian, we're seeing the dawn of the modern world in a very real sense. The patterns of predation and prey, of competition and cooperation, of adaptation to different environments, all these fundamental aspects of ecology were being established. The seas were workshops where evolution learned its craft, where the basic rules of life in water were being written for the first time. And all of this happened in warm, shallow seas under cloudless skies, in water that would have felt pleasant if you could have somehow dipped your hand into it, in an ocean that was vibrant with life discovering its infinite possibilities. There's something magical about bioluminescence, about creatures that can generate their own light in the darkness. We think of it as a modern phenomenon, perhaps, something associated with deep-sea anglerfish or fireflies on a summer evening. But bioluminescence is ancient, far more ancient than most people realize. It appears in the fossil record much further back than scientists once believed, and its evolution tells us something beautiful about how life adapts to the challenges of living in darkness. Recent research has pushed the origins of animal bioluminescence back to approximately 540 million years ago, right around the time of the Cambrian explosion we just explored. The creatures responsible for this ancient light show were octocorals, a group that includes soft corals, sea pens and sea fans. These animals, with their eightfold symmetry and branching tree-like structures, began producing light in the depths of the Cambrian seas, making them the oldest known bioluminescent animals. This discovery pushed back the timeline for bioluminescence by nearly 300 million years. Previously, scientists thought the oldest bioluminescent animals were tiny crustaceans called ostracods that lived about 267 million years ago. But the octocorals beat them to it by 250 million years, glowing softly in the darkness of the ancient ocean long before ostracods even existed. Why did these early octocorals develop the ability to produce light? Scientists aren't entirely certain, which makes the question all the more intriguing. Modern octocorals typically glow only when they're disturbed, when something bumps into them or brushes against their polyps. This has led to what researchers call the burglar alarm hypothesis. The idea is that bioluminescence might startle a predator or attract an even larger predator that might eat the first predator, essentially calling for help in the form of a glowing distress signal. It's a clever defensive strategy if that's truly how it works. But there's another possibility. Bioluminescence might have originally evolved not for communication or defense, but as a kind of biological side effect of dealing with oxygen. In the early oceans, as photosynthetic organisms began producing oxygen, this highly reactive molecule posed a challenge. Oxygen can damage cells through a process called oxidative stress. Some of the same biochemical pathways that helped early organisms detoxify oxygen involved molecules that, under the right circumstances, could produce light. So bioluminescence might have started as a waste product, a glow that resulted from necessary chemistry rather than something that evolution specifically selected for. Only later would organisms have co-opted this glow, refined it, and put it to use for communication, hunting, or defense. Imagine these early octocorals, branching and soft, anchored to rocks in the Cambrian seas. During the day, they would have been unremarkable, swaying gently in the currents, their polyps extended to capture tiny particles of food from the passing water. But at night, or in the deeper waters where sunlight couldn't penetrate, these creatures would have glowed with a soft blue-green light when disturbed. A fish brushing past them would have triggered a cascade of light rippling through the colony. A predator investigating them for a potential meal would have suddenly been illuminated, exposed, possibly attracting unwanted attention from its own predators. This light wouldn't have been bright, not like a flashlight or even a candle. It would have been subtle, ghostly, barely visible in the clearer water near the surface, but quite noticeable in the darkness of the deep. The chemical reaction that produces bioluminescence in these corals involves a molecule called colentrazine and an enzyme that adds oxygen to it, creating an excited state that releases energy in the form of light. It's an elegant piece of biochemistry, efficient and reliable, requiring no external energy source beyond the chemicals the organism itself produces. As time went on, bioluminescence evolved independently in many different lineages. By the Devonian period, about 400 million years ago, it had appeared in various groups. By the Carboniferous, 300 million years ago, it was becoming widespread. Each time it evolved, it solved the same basic chemical problem: how to produce light without heat, how to create a cold glow that wouldn't waste energy or damage tissues. Different organisms arrived at different solutions, using different molecules and different enzymes, but the end result was always the same: a soft, cool light emerging from living tissue. In the ancient oceans, bioluminescence served many purposes. Some creatures used it to attract mates, flashing patterns that signaled their species, their sex, their readiness to reproduce. Others used it to lure prey, dangling a glowing lure in the darkness to attract curious fish or crustaceans. Still others used it for camouflage, a technique called counter-illumination, where light on the belly of a creature matches the dim light filtering down from above, effectively erasing their silhouette and making them invisible to predators looking up from below. The deep seas of the Paleozoic and Mesozoic eras would have been filled with these lights, not constantly. Most bioluminescent organisms only produce light when they need to conserve the chemicals involved, but frequently enough that a descent into the abyss would have revealed a galaxy of small moving lights. Here a jellyfish pulsing with pale luminescence. There a worm leaving a trail of glowing mucus. Everywhere the tiny pinprick lights of countless microscopic organisms, each one smaller than a grain of sand, collectively creating a faint, pervasive glow. Dints of largulates, single-celled organisms that have existed for hundreds of millions of years, develop their own form of bioluminescence. When disturbed by waves or by swimming creatures, they flash with blue light. In sufficient numbers, they can turn breaking waves into ribbons of glowing blue-white light, a phenomenon that still occurs today in certain parts of the ocean. Ancient mariners, if there had been any in the Mesozoic seas, would have witnessed this same spectacle: bioluminescent dints of largulates lighting up the wake of swimming reptiles, creating trails of cold fire in the darkness. The evolution of bioluminescence also changed predation. A creature that could produce its own light could hunt in complete darkness, illuminating prey with a sudden flash or using a steady glow to search the water for food. This gave rise to counter-adaptations, with prey species developing ways to hide from or confuse bioluminescent predators. Some evolved dark pigmentation to absorb light rather than reflect it. Others developed the ability to sense bioluminescent light and flee before a predator could get close enough to strike. As fish diversified during the Devonian and later periods, they inherited and further refined bioluminescence. By the Cretaceous, there were probably hundreds or thousands of species of bioluminescent fish, each with their own patterns and purposes for their light. Some had photophores, specialized light-producing organs, arranged in lines along their bodies. Others had light organs near their eyes, effectively giving them headlights for navigating the darkness. Still others had large photophores on their bellies for counter-illumination, or glowing lures dangling from modified fins. Recent research has revealed that biofluorescence in fish, a related but different phenomenon, where creatures absorb blue or ultraviolet light and re-emit it as a different color, dates back at least 112 million years to the early Cretaceous. This discovery suggests that the oceans of the dinosaur era were not only filled with bioluminescent light, but also with the vibrant, transformed light of biofluorescence. A coral reef in the Cretaceous seas would have looked dramatically different under different wavelengths of light, with some creatures glowing red, others green, still others yellow or orange, each responding to the environment in their own unique way. There's something deeply soothing about imagining these glowing seas, not the bright, harsh light of the modern world, but soft, gentle glows appearing and disappearing in the darkness. A slow pulse of blue-green light from a disturbed coral, the faint shimmer of dinoflagellates in a breaking wave, the steady glow of a fish's photophore as it searches for prey. These lights existed for hundreds of millions of years, long before humans evolved to witness them. They were the first lights in the ocean, the first biological illumination on a planet that had been dark except for the sun, moon, stars, and occasional lightning. And they still exist today, of course. Bioluminescence hasn't disappeared. It remains one of the most common adaptations in the ocean, with an estimated 75% of deep-sea creatures possessing the ability to produce light. When we see bioluminescence in modern seas, we're witnessing a phenomenon that stretches back 500 million years. A connection to the earliest days of complex life on Earth. The chemistry is the same. The purpose might be similar. The glow we see today is the glow that lit the ancient oceans, unchanged and unchanging. A light that has been shining continuously through countless extinctions and ice ages and the rise and fall of entire ecosystems. In its constancy and its antiquity, bioluminescence reminds us that some adaptations are so successful, so elegant, that evolution preserves them almost unchanged across unimaginable spans of time. The octocorals glowing in the Cambrian seas 500 million years ago would recognize their distant descendants glowing in the Pacific today. The chemistry would be familiar. The purpose would be the same. And in that continuity, in that thread of light stretching across 500 million years, there's something profoundly peaceful. Between the ancient continents of Gondwana in the south and Laurasia in the north, a great ocean stretched from west to east across much of the planet. This was the Tethys Ocean, named for the Greek water goddess who was sister and consort to Oceanus. It existed for hundreds of millions of years, shifting and changing as the continents slowly drifted, but always maintaining its fundamental character, a warm tropical sea that connected distant parts of the world. The Tethys Ocean was not a single, unchanging body of water. Geologists actually recognize several different phases: the Paleo-Tethys Ocean from the Devonian through the Triassic, the Meso-Tethys from the Permian through the Cretaceous, and the Neo-Tethys or simply Tethys Ocean from the Triassic through the Cenozoic. Each of these phases represented the ocean that existed between the major continental masses as they slowly rearranged themselves through plate tectonics. But for simplicity, and for the purposes of our peaceful journey tonight, we can think of them collectively as the Tethys, a warm seaway that persisted in one form or another for perhaps 300 million years. The Tethys was predominantly a tropical ocean. It lay mostly between 30 degrees north and 30 degrees south latitude, the warm belt of the planet where the sun's rays strike most directly. The water temperature throughout much of the Tethys would have been delightfully warm, 25 to 30 degrees Celsius at the surface, comfortable enough to swim in year-round. There were no seasons as we know them in the central Tethys, just endless summer, day after day, century after century, millennium after millennium. The sky would have been mostly clear, with occasional build-ups of clouds that brought brief, intense tropical rainstorms before dissipating again. The floor of the Tethys Ocean was relatively shallow in many areas, especially along the margins where it lapped against the continents. Extensive coral reefs developed in these shallow waters, building vast limestone platforms that stretched for hundreds of miles. These were not quite like modern coral reefs. The species were different, the ecology was different, the chemistry of the water was slightly different, but the basic principle was the same. Countless tiny coral polyps, each one cooperating with symbiotic algae, built calcium carbonate skeletons that accumulated over time into massive structures. These reefs were oases of life, home to countless species of fish, crustaceans, mollusks, and other creatures. Ammonites were particularly abundant in the Tethys Ocean. These cephalopods, relatives of modern squid and octopuses, lived inside coiled shells that ranged from tiny to enormous. Some ammonites were no bigger than a coin, while others grew shells several feet across. They swam through the Tethys waters by jet propulsion, squirting water out of their bodies to push themselves along. Their shells were divided into chambers, with the animal living in the largest, outermost chamber, and the others filled with gas for buoyancy control. By adjusting the ratio of gas to liquid in these chambers, an ammonite could rise or sink in the water, hovering at whatever depth suited it best. During the Jurassic period, roughly 200 to 150 million years ago, the Tethys Ocean was home to some of the most spectacular marine reptiles that ever lived. Ichthyosaurs, looking remarkably like dolphins despite being reptiles, hunted in the open waters. They were fast, streamlined, powerful swimmers with large eyes for spotting prey. Some species could dive deep, chasing squid and fish into the darker waters below the sunlit zone. Others stayed near the surface, breaching and breathing air regularly, perhaps traveling in pods like modern dolphins. Plesiosaurs all swam through the Tethys, though they were quite different from ichthyosaurs. They had long necks in many cases, small heads, and 4 large flippers. They used to fly through the water with a motion not unlike that of a sea turtle. Some plesiosaurs had necks longer than their bodies, giving them a bizarrely out-of-proportion appearance. They probably fed on fish, using their long necks to reach into schools and snatch prey before the school could scatter. Others had shorter necks but massive heads, making them more like ambush predators that could tackle larger prey. The mosasaurs came later, dominating the Tethys during the late Cretaceous period, roughly 90 to 66 million years ago. These were actually more closely related to modern monitor lizards than to the other marine reptiles, having evolved from land-dwelling ancestors that returned to the sea. Mosasaurs were powerful predators, some growing to more than 50 feet in length. They had long snouts lined with sharp teeth, muscular bodies, and paddle-like limbs for swimming. They probably hunted ammonites, fish, sea turtles, and even other marine reptiles. Their jaws were so powerful they could crack the shells of ammonites and sea turtles with ease. But the Tethys wasn't only about these large, dramatic creatures. The bulk of life in this ancient ocean consisted of smaller organisms. Countless species of fish schooled in the upper waters, feeding on plankton or hunting each other. Squid and their relatives darted through the water column, changing color, squirting ink, displaying remarkable intelligence despite their short lives. Crustaceans of all kinds crawled over the seafloor or swam through the water, playing crucial roles in the ecosystem as both predators and prey. The sediments accumulating on the floor of the Tethys Ocean were largely limestone and chalk, formed from the shells and skeletons of countless marine organisms. When these creatures died, their hard parts settled to the bottom, slowly building up layers of calcium carbonate. Over millions of years, these layers compacted into rock. Much of this rock still exists today. The limestone cliffs of the European Alps, for instance, formed from Tethyan seafloor that was later uplifted and compressed when Africa and Europe collided. The White Cliffs of Dover in England are made of chalk that accumulated on the floor of a northern extension of the Tethys. When you look at these formations today, you're seeing the remains of an ancient ocean, solidified into stone but still bearing the marks of its origin. The Tethys Ocean played a crucial role in regulating Earth's climate throughout its existence. It allowed warm water from the tropics to circulate toward higher latitudes, distributing heat and moderating temperatures across much of the northern hemisphere. During periods when the Tethys was particularly wide and deep, it functioned almost like a conveyor belt, moving warm surface water east and west, mixing with waters from other ocean basins, helping to keep the poles warmer than they would otherwise have been. During the Cretaceous period, when global temperatures were particularly high, the Tethys was exceptionally warm. Sea surface temperatures in the tropical Tethys might have exceeded 35 degrees Celsius in some locations, warmer than most tropical oceans are today. These hot waters were somewhat depleted in oxygen, especially in the deeper layers, leading to periods of anoxia when the deep water became essentially dead zones. When this happened, organic matter falling from the surface waters didn't decompose normally. Instead, it accumulated on the seafloor, eventually forming organic-rich sediments that would later become oil and natural gas deposits. Much of the petroleum we extract today originally formed in the Tethys Ocean during these anoxic periods. As the continents continued to drift, the Tethys gradually closed. India, breaking away from the southern landmasses, drifted north and eventually collided with Asia about 50 million years ago. This collision began the process of squeezing shut the Tethys, pushing up the seafloor to create the Himalayan mountain range. Africa also moved north, colliding with Europe and Arabia with Asia, further constricting the ocean. By about 6 million years ago, the Tethys had been almost entirely closed, leaving only remnants behind. Today, those remnants include the Mediterranean Sea, the Black Sea, and the Caspian Sea. These are the last pieces of the once vast Tethys Ocean, isolated landlocked seas, or nearly landlocked seas, that still bear some traces of their ancient heritage. The Mediterranean, in particular, retains something of the character of the Tethys: warm, relatively calm, rich in life, connecting distant shores. When ancient traders sailed across the Mediterranean, when explorers mapped its coasts, they were navigating a descendant of the Tethys, following routes that marine creatures had swum for hundreds of millions of years before the first humans existed. The Tethys Ocean, in all its phases and incarnations, was a highway for life. Species could spread from one end to the other, given enough time and the right conditions. The warm water was generally suitable for tropical and subtropical organisms throughout its vast length. This connectivity meant that innovations, adaptations, and new body plans that evolved in one part of the Tethys could eventually spread throughout it, enriching the entire ocean. The Tethys was not isolated or stagnant, but rather a thoroughfare, a living seaway where life flowed along with the currents. In its warmth, its stability, its vast extent, and its long persistence, the Tethys Ocean represents a kind of golden age of ancient seas. It was there for so long, providing such consistent conditions, that evolution had time to refine adaptations to an extraordinary degree. The creatures that lived in the Tethys were superbly adapted to their environment, having had hundreds of millions of years to perfect their survival strategies. And when we look at the fossils from this ocean, when we study the rock layers that once were its floor, we can still sense something of that ancient warmth, that tropical perfection, that long, slow dream of summer seas under endless blue skies. If we could choose any time in Earth's history to explore truly warm oceans, it would almost certainly be the Cretaceous period. This was Earth as a hothouse, a greenhouse world where temperatures were dramatically higher than anything in recent geological history. From about 145 million years ago to 66 million years ago, the Cretaceous seas were some of the warmest waters that ever existed on our planet. There was no ice anywhere, not at the poles, not on mountains, nowhere. The entire Earth was warm, and the oceans reflected and amplified that warmth. Scientists now know that tropical sea surface temperatures during parts of the Cretaceous reached 32 to 35 degrees Celsius, and possibly even higher in some locations and time periods. To put that in perspective, most modern tropical oceans average around 25 to 28 degrees. The Cretaceous seas were like bathwater, comfortably warm anywhere you went, even more so in the tropics. You could have floated in these waters indefinitely without feeling cold. The warmth would have enveloped you, relaxed your muscles, slowed your breathing, induced a state of deep, dreamy comfort. Even more remarkable, the deep ocean was warm during the Cretaceous, while today's deep seas are near freezing, around 2 degrees Celsius in most places. The deep waters of the Cretaceous Ocean were 15 to 20 degrees warmer. That means that even at depths of several thousand meters, the water was warmer than a modern temperate surface ocean. The entire water column from surface to abyss was suffused with warmth. There were no cold currents from the poles bringing frigid water into the deep basins, because the poles themselves weren't cold. Everything was warm. This warmth had profound effects on ocean circulation. Without cold, dense water sinking at the poles to drive deep currents, the Cretaceous oceans had a different pattern of circulation. Surface currents were driven by wind and the Earth's rotation, much as they are today, but deep circulation was sluggish, slow, and driven more by differences in salinity than by temperature. Warm, salty water from tropical shallow seas might sink and spread slowly through the deep ocean, but it did so without the vigorous overturning that characterizes modern ocean circulation. The result was an ocean that was more stratified, with distinct layers that mixed slowly. The high temperatures were caused by several factors working together. Atmospheric carbon dioxide levels were very high during much of the Cretaceous, perhaps 3 to 6 times higher than pre-industrial levels, and sometimes even higher than that. This created a powerful greenhouse effect, trapping heat and raising temperatures globally. Volcanic activity was also intense during this period. Massive volcanic provinces erupted in various parts of the world, releasing enormous amounts of lava and gases. The most famous of these is the Ontong Java Plateau in the Western Pacific, a massive volcanic structure as large as Alaska that formed during the Cretaceous. These eruptions not only added more carbon dioxide to the atmosphere but also displaced seawater, causing sea levels to rise dramatically. And sea levels were indeed much higher during the Cretaceous than they are today, perhaps 200 meters higher at some points. This meant that vast areas of what are now continents were underwater. Shallow seas flooded across the interiors of landmasses, creating epicontinental seas that were perfect habitats for marine life. One of the most famous of these was the Western Interior Seaway, a shallow sea that split North America in two, running from the Arctic Ocean to the Gulf of Mexico. At its largest, this seaway was 600 miles wide and over 2,000 miles long, covering much of what is now the Great Plains. The Western Interior Seaway was shallow, mostly less than 800 meters deep and often much shallower than that. Its waters were bath-warm, especially in the tropical and subtropical portions. The seafloor was covered in soft muds and silts brought down by rivers from the surrounding highlands. These sediments were rich in nutrients, supporting abundant life. Plankton bloomed in the upper waters. Schools of fish filled the water column, and swimming through these warm, shallow seas were the marine reptiles we've already mentioned: mosasaurs, plesiosaurs, and numerous others. Sea turtles also thrived in the Cretaceous oceans. Some species grew to enormous sizes. Archelon, for instance, could reach over 13 feet in length, making it the largest sea turtle that ever lived. Unlike modern sea turtles, which have hard shells, Archelon had a leathery carapace, more flexible, but offering less protection. It probably spent most of its time in the open ocean, coming to shores to lay eggs. Its powerful flippers could carry it across thousands of miles of warm water, following currents and food sources, living a life of constant, gentle swimming through tropical seas. Sharks had been around for hundreds of millions of years by the Cretaceous, but this period saw them diversify into many new forms. Some were similar to modern sharks, fast predators with streamlined bodies and sharp teeth. Others were more specialized. There were forms adapted to crushing shellfish, others to filtering plankton, still others to hunting in particular environments. One remarkable species was Cretox irena, sometimes called the Ginsu shark for its blade-like teeth. This was a large, fast predator that could grow to 25 feet in length, hunting fish and even marine reptiles in the Cretaceous seas. The warmth of the Cretaceous oceans extended all the way to the poles. At the North and South Poles, sea surface temperatures may have been 15 to 20 degrees Celsius, comparable to modern temperate regions. This meant that polar seas were habitable for creatures that we think of as tropical or subtropical. There's evidence of plesiosaurs and other marine reptiles living in polar waters, tolerating the long polar night in winter and the continuous daylight in summer, feeding on fish and squid that were themselves adapted to these unusual conditions. The forests of the Cretaceous extended almost to the poles as well, with conifers and other plants growing in regions that are today tundra or ice-covered. Rivers flowed from these forests into the polar seas, bringing nutrients and sediment. The coastal waters would have been particularly productive, with abundant food supporting rich ecosystems. During the summer months, when the sun never set, productivity would have been extraordinary, with phytoplankton blooming in massive quantities, supporting a food web that extended up to the largest predators. But this warmth came with a cost. The warm Cretaceous oceans were oxygen poor, especially in the deeper layers. Warm water can't hold as much dissolved oxygen as cold water, a simple fact of chemistry that had profound implications. During certain periods, much of the deep ocean became anoxic, devoid of oxygen, essentially dead to any creature that needed to breathe. When this happened, dead organic matter falling from the surface couldn't decompose properly. Instead of being broken down by bacteria and recycled back into the food web, it accumulated on the seafloor as black, organic-rich muds. These oceanic anoxic events, as scientists call them, occurred multiple times during the Cretaceous. They might have been triggered by volcanic eruptions that released massive amounts of carbon dioxide, raising temperatures and disrupting ocean circulation. Or they might have been caused by other factors, changes in sea level, shifts in ocean currents, or cascading effects from changes on land. Whatever the cause, these events left distinctive markers in the geological record, layers of black shale, rich in organic carbon, representing times when large portions of the ocean essentially held their breath. Yet despite these periodic crises, or perhaps because of them, the Cretaceous seas were home to spectacular diversity. The warm water, the abundant nutrients from river runoff, the extensive shallow seas all combined to create ideal conditions for life. Every ecological niche was filled. Every possible way of making a living in the ocean had creatures adapted to it, from the smallest plankton to the largest marine reptiles, from filter feeders to apex predators. The Cretaceous seas were as rich and diverse as any ocean has ever been. The sky above these warm waters would have looked much like a modern tropical sky, blue, often cloudless, sometimes punctuated by towering cumulus clouds that built up in the afternoon heat and released brief but intense rainstorms. The water itself would have been clearer than modern oceans in many areas, since there was less runoff from barren, eroding continents and more extensive coral reefs to filter and clean the water. Visibility might have been extraordinary, 50 or 100 meters in the clearest areas, allowing sunlight to penetrate deep and support photosynthetic life far below the surface. At night, the stars would have wheeled overhead much as they do today, though the constellations would have been slightly different due to the slow drift of stars over millions of years. The moon would have been closer to Earth than it is now, appearing slightly larger in the sky, creating stronger tides that might have been particularly noticeable in the shallow epicontinental seas. These tides would have ebbed and flowed, creating currents, exposing and submerging tidal flats, providing rhythm to the lives of countless creatures living in the shallows. The Cretaceous period ended catastrophically 66 million years ago with the impact of a massive asteroid near what is now the Yucatan Peninsula in Mexico. The impact and its aftermath killed off many species, including all the non-avian dinosaurs on land and most of the marine reptiles in the sea. But for the 80 million years before that moment, the Cretaceous seas had been an almost paradisiacal environment for marine life, warm, extensive, rich in food, home to creatures of every size and shape. They represent a kind of peak for ocean life, a time when the seas truly dominated Earth, and when being in the water was as comfortable and pleasant as an environment could be. The ancient seas moved in rhythms, patterns that repeated over hours, days, years, and even millions of years. These rhythms shaped the lives of every creature that lived in the water, creating a predictable framework of change that evolution could adapt to. The most immediate of these rhythms were the tides, the daily rise and fall of sea level caused by the gravitational pull of the moon, and to a lesser extent the sun. But tides in the ancient oceans were different from tides today in one crucial way. The moon was closer to Earth. When the moon first formed around 4.5 billion years ago, it was perhaps 15 times closer than it is now. At that distance, the tides it raised would have been enormous, perhaps hundreds of meters high, though the Earth was also spinning much faster then, completing a rotation in just 5 or 6 hours rather than the 24 hours we experience today. As time passed, the moon slowly spiraled outward, moving away from Earth at a rate of about 1.5 inches per year. This is still happening today, very gradually. During the Cambrian period, about 500 million years ago, the moon was significantly closer than it is now, and the Earth's day was only about 21 hours long. This meant the tides were stronger and more frequent. Coastal areas would have experienced the full range of tidal variation every 10 or 11 hours rather than the 12.5 hours of today. For creatures living in tidal zones, this created a more compressed cycle of exposure and immersion, wet and dry, access to food and vulnerability to predators. In the deep ocean, far from shore, tides weren't directly noticeable. The water level rose and fell, but a creature swimming in the open sea wouldn't sense this change. However, tides created currents, subtle flows of water that responded to the moon's pull. These tidal currents mixed water masses, brought nutrients up from the deep, and created predictable patterns that some creatures could follow or exploit. Even in the deepest ocean, the influence of the moon was present, a gentle reminder that Earth doesn't exist in isolation but is part of a larger system. Longer cycles also influenced the ancient seas. The Earth's orbit around the Sun is not perfectly circular but slightly elliptical, and this shape changes over time in predictable cycles. The tilt of Earth's axis also changes, oscillating between more tilted and less tilted over periods of tens of thousands of years. These astronomical cycles, called Milankovitch cycles after the scientist who first described them, affect how much sunlight reaches different parts of Earth and when. During periods when the Earth's tilt is greater, seasonal differences are more extreme. During periods when the orbit is more circular, seasonal differences are less pronounced. These cycles influenced ocean temperatures, ice formation during cooler periods, and the circulation of currents. They also affected the distribution of organisms. During a period when northern summers received more sunlight, organisms adapted to warm water could spread farther north. When the cycle shifted and northern summers grew cooler, these same organisms would retreat toward the equator again. Over hundreds of thousands or millions of years, these oscillations shaped evolution, creating selective pressures that favored organisms able to tolerate a range of conditions or able to migrate to track their preferred environment. Ocean currents in the ancient seas followed patterns determined by wind, the Earth's rotation, and the distribution of continents. The largest currents were the Great Gyres, circular flows that moved water around ocean basins. In the northern hemisphere, these gyres rotated clockwise, while in the southern hemisphere they rotated counterclockwise, a consequence of the Coriolis effect caused by Earth's rotation. Warm water moved away from the equator along the western edges of ocean basins, while cooler water returned toward the equator along the eastern edges. These currents were highways for marine life. Creatures could drift with them, allowing the water to carry them vast distances without expending much energy. Fish might follow currents to spawning grounds or feeding areas. Planktonic organisms could complete their entire lives while being transported hundreds or thousands of miles by currents. Seeds and spores of marine plants could spread across entire oceans, carried by these reliable flows. In some ways, the current systems of ancient oceans were simpler than today's, especially during times like the late Paleozoic when Panthalassa dominated the planet. With fewer continents to complicate the flow, currents in Panthalassa probably followed relatively straightforward patterns: westward flow at the equator, driven by trade winds; poleward flow along the eastern edge of Pangaea; eastward flow in the temperate zones, driven by westerly winds; and equatorward return flow along the western side of the ocean. These patterns would have persisted for millions of years, creating a stable framework for ocean life. But as continents shifted and new ocean basins opened, current patterns changed. The opening of the Atlantic Ocean, beginning in the Jurassic and continuing through the Cretaceous and into the Cenozoic, created new opportunities for currents to flow north-south between the Americas on one side and Europe and Africa on the other. The collision of India with Asia and the closing of the Tethys Ocean fundamentally altered current patterns in what would become the Indian Ocean. Each tectonic change rippled through the ocean system, creating new currents, eliminating old ones, connecting previously isolated water masses, or separating regions that had once been connected. Upwelling was another crucial process in ancient oceans, just as it is today. Upwelling occurs when deep, nutrient-rich water rises to the surface, usually due to winds pushing surface water away from a coast. The deep water that replaces it brings with it dissolved nutrients that have accumulated in the dark depths. When these nutrients reach the sunlit surface waters, they fertilize phytoplankton blooms, which in turn feed zooplankton, which feed fish, which feed larger predators. Upwelling zones are among the most productive regions in the ocean, supporting enormous populations of marine life. In the ancient seas, upwelling zones would have been just as important. Coastal regions where winds regularly blew offshore would have been hotspots of productivity. Creatures would have congregated in these areas to take advantage of the abundant food. Seasonal changes in wind patterns would have created seasonal upwelling, leading to regular cycles of abundance and scarcity that organisms evolved to anticipate and exploit. The chemistry of the ancient oceans also cycled. During some periods, the oceans were more alkaline, during others more acidic. Carbon dioxide dissolved from the atmosphere could make seawater more acidic, while weathering of rocks on land and the deposition of calcium carbonate by organisms could make it more alkaline. These changes happened slowly, over millions of years, but they affected which organisms could build shells, which could grow reefs, which could thrive, and which would struggle. Oxygen levels in the ocean also varied through time. During the Cambrian, oxygen was relatively low, limiting how large animals could grow. As plants colonized the land and photosynthetic organisms flourished in the oceans, oxygen levels rose. By the Carboniferous period, atmospheric oxygen reached perhaps 35%, higher than today's 21%. This high oxygen allowed some arthropods on land to grow to enormous sizes, and it probably affected marine life as well, though the effects were less dramatic, since oxygen levels in water are always much lower than in air. All of these rhythms, tidal, seasonal, astronomical, chemical, created a complex tapestry of change that defined life in the ancient oceans. Nothing was truly static. Everything cycled, oscillated, varied. Yet these changes were mostly gradual, predictable, reliable. An organism could evolve to anticipate the tides, to follow the seasons, to track the currents. The patterns repeated year after year, century after century, giving life the time it needed to adapt, to optimize, to find its place in the endless cycles of the sea. And in those cycles, there was a kind of peace. The water rose and fell with the tides, but it always came back. The currents flowed and ebbed, but they followed known paths. The seasons turned, but they turned in the same order every time. In the midst of constant change, there was profound constancy, a rhythm as reliable as breath, as soothing as a heartbeat, as certain as the turning of the earth itself. The ancient seas were home to creatures of astonishing variety, from microscopic plankton to marine reptiles larger than school buses. Each of these organisms played a role in the ecosystem. Each was adapted to its particular way of life, and each tells us something about the environment it lived in. Let's meet some of these creatures, not by cataloging every species, but by getting to know a few representatives, understanding their lives, imagining their experience of the ancient oceans. Ammonites deserve special attention, not just because they were so diverse and abundant, but because they're so alien yet somehow familiar. These were cephalopods, relatives of modern squids and octopuses, but instead of being soft-bodied, they lived inside shells. These shells were coiled, usually in a flat spiral, though some species had more complex, three-dimensional coil patterns. The exterior of the shell was often ornamented with ribs, spines, or knobs, giving each species a distinctive appearance. Inside its shell, an ammonite looked something like a squid. It had tentacles for catching prey, a parrot-like beak for biting, and a siphon for jet propulsion. But unlike a squid, which can move freely in any direction, an ammonite was constrained by its shell. It probably swam horizontally, with the shell coiled behind it, moving forward by expelling water through its siphon. The shell provided protection from predators, and also helped with buoyancy control, allowing the ammonite to hover at a specific depth without constantly swimming. Ammonites ranged in size from smaller than a coin to several feet in diameter. The largest known ammonite, Parapazosia sepenredensis, had a shell that could exceed 7 feet across, making it one of the largest shells ever formed by any animal. Imagine encountering such a creature in the Cretaceous seas, a coiled shell the size of a wagon wheel, with tentacles extending out, eyes that could track your movement, a living, intelligent animal carrying its entire home on its back. These creatures were incredibly successful. Ammonites existed for over 300 million years, from the Devonian period through to the end of the Cretaceous, and during that time they evolved into thousands of species. They lived in all the world's oceans, from shallow coastal waters to the open ocean, from the tropics to the poles. Their fossils are so common and so varied that paleontologists use them as index fossils, markers that help date the rocks in which they're found. The presence of certain ammonite species can pinpoint when a rock layer was deposited to within a few million years, sometimes even less. Then there were the giant predators, the marine reptiles that dominated the Mesozoic seas. We've mentioned them before, but it's worth spending more time with them. Ichthyosaurs, for instance, were remarkably dolphin-like in appearance and probably in behavior. They had streamlined bodies, a dorsal fin, and a tail with horizontal flukes. Their limbs had evolved into flippers. Their eyes were enormous, among the largest eyes of any animal ever. some species having eyes the size of dinner plates. These massive eyes suggest they hunted in deep water where light was dim, or at night when their superior vision would give them an advantage over prey. Some ichthyosaurs could grow to over 65 feet long, though most were smaller, in the 10 to 20 foot range. They gave birth to live young rather than laying eggs, with some fossils even preserving adult females with babies inside them or in the act of giving birth. These creatures were fully aquatic, probably never coming to land even to reproduce. They swam through the ancient seas much as dolphins do today, fast and agile, likely traveling in groups, possibly even communicating with each other through sounds or body language. Plesiosaurs were quite different. Rather than being streamlined, many had large, heavy bodies, long necks, small heads, and 4 large flippers. They swam by flapping these flippers in a motion similar to underwater flight, like sea turtles but more powerfully. The long neck seems awkward to us, but it was probably an advantage in hunting. A plesiosaur could approach a school of fish with its body positioned below, keeping the large body at a distance, then dart its small head into the school to grab prey before the fish realized the danger. Not all plesiosaurs had long necks. The plesiosaurs, a group within the plesiosaur family, had short necks and massive heads, some with skulls over 8 feet long. These were the apex predators of their time, capable of taking down large prey, including other marine reptiles. Kronosaurus, one of the largest plesiosaurs, could reach 40 feet in length, with a skull alone reaching 10 feet. Its teeth could grow up to 12 inches long. This was an animal built for power, for crushing and tearing, for dominating its environment through sheer size and strength. Mosasaurs came later, appearing in the Cretaceous and quickly becoming the dominant marine predators after the ichthyosaurs and most plesiosaurs had declined. They evolved from land-dwelling lizards, probably entering the water in pursuit of prey or to escape predators, and over millions of years became so well adapted to aquatic life that they could never leave it. The largest mosasaurs reached 50 feet in length, though most were smaller. They had powerful tails for swimming, paddle-like limbs, and jaws that could unhinge to swallow large prey. But not all creatures in the ancient seas were large and dramatic. The majority of life consisted of smaller organisms. Schools of fish filled the water column. Each species adapted to a particular ecological niche. Some fed on plankton, filtering tiny organisms from the water as they swam. Others hunted smaller fish, using speed and agility to catch their prey. Still others were scavengers, feeding on dead organisms that fell from the upper waters to the seafloor. Crustaceans were everywhere, swimming forms like ancient relatives of shrimp, bottom-dwelling forms like early crabs and lobsters, and countless others filling every imaginable niche. Some were predators, some herbivores, some scavengers, some lived on coral reefs, others in the open ocean, still others in the deep sea. Their exoskeletons provided protection and support, and their jointed appendages gave them remarkable versatility in movement and manipulation. Sea urchins grazed on algae, using their tube feet to crawl slowly across rocks and their specialized mouthparts to scrape food from surfaces. Starfish were predators, using their hydraulic tube feet to pry open the shells of mollusks or grip onto prey. Sea cucumbers crawled across the seafloor, using tentacles around their mouths to gather organic particles from the sediment, essentially vacuum cleaning the ocean floor. In the water column, jellyfish pulsed slowly along, trailing tentacles loaded with stinging cells to capture prey. Comb jellies, similar but unrelated to jellyfish, moved by beating rows of cilia that refracted light into rainbow colors as they swam. Salps, colonial tunicates, formed long chains in the water, filtering plankton and reproducing both sexually and asexually in complex life cycles. All of these creatures, from the massive mosasaurs to the microscopic plankton, were part of interconnected food webs. Energy from the sun was captured by photosynthetic organisms, transferred to herbivores, then to carnivores, then to larger carnivores, with decomposers breaking down dead organic matter at every level and recycling nutrients back into the system. The ancient seas functioned as ecosystems just as modern oceans do, with the same basic principles of energy flow and nutrient cycling, though the specific species playing each role were often very different. And everywhere, in every habitat, at every depth, life filled the available space. There were no empty niches in the ancient seas, no opportunities that went unexploited. Evolution, given hundreds of millions of years to work, had found a way to make a living in every conceivable environment. The diversity of ancient marine life rivaled, and in some cases exceeded, the diversity we see in modern oceans, a testament to the incredible creative power of evolution and the richness of the marine environment. Beneath the waters of the ancient seas, sediment accumulated slowly, particle by particle, year after year, century after century. This process of sedimentation has continued since Earth's first oceans formed, and it's one of the most important geological processes on the planet. The sediments that settled on ancient seabeds tell us almost everything we know about those lost oceans. They preserve fossils, record climate changes, document extinctions and recoveries, and eventually, after millions of years of accumulation and compression, transform into the sedimentary rocks we study today. In the shallow tropical seas of the Cambrian, Silurian, and other periods, much of the sediment was composed of calcium carbonate. This material came from the shells and skeletons of countless marine organisms. When a creature with a calcium carbonate shell died, its soft tissues quickly decomposed or were eaten by scavengers, but the shell remained. It might be broken by waves or crushed by predators, but fragments persisted. These fragments settled to the seafloor, accumulating in layers, mixing with sediment particles washed in from land, slowly building up. In quiet areas where currents were gentle, this sediment accumulated in thin, even layers, creating a beautiful record of time passing. Each layer represents a particular moment in history, and if you could examine them closely enough, you might be able to count them like tree rings, each one recording a year or a season. But the compression and transformation of sediment into rock usually obscures this level of detail. What we see instead are thicker layers representing thousands or millions of years of accumulation. The type of sediment that accumulated depended on the environment. In warm, clear, shallow seas with abundant coral reefs, the sediment was primarily limestone, bright and white when freshly exposed, made almost entirely of calcium carbonate. In deeper, cooler waters, different organisms contributed to the sediment. The shells of foraminifera, microscopic single-celled organisms that float in the water, rained down constantly. So did the tiny plates of coccolithophores, single-celled algae covered in calcium carbonate armor. These organisms were so abundant that their remains formed vast chalk deposits. The famous white cliffs of Dover are made of chalk that accumulated on the floor of a Cretaceous sea, formed entirely from the shells of countless tiny organisms. In other areas, the sediment was mud or clay, fine particles eroded from the land and carried to the sea by rivers. This terrigenous sediment, as it's called, contained no fossils of its own but could preserve the fossils of creatures that lived in or on it. The soft mud of ancient seabeds was a perfect medium for fossilization. When an organism died and settled into the mud, it was quickly covered by more sediment, protecting it from scavengers and decomposition. Over time, minerals dissolved in the water percolated through the sediment and replaced the original material of the fossil, turning it to stone while preserving its shape in exquisite detail. Some of the best preserved fossils in the world come from ancient seabeds where conditions were just right. The Burgess Shale in Canada, for instance, preserves Cambrian creatures in such detail that you can see their internal organs, their digestive systems, even the last meals in their stomachs. This level of preservation is extremely rare and requires very specific conditions: rapid burial in fine sediment, absence of oxygen to prevent decomposition, and subsequent lack of disturbance that might crush or destroy the fossils. But when it occurs, it provides an almost miraculous window into the past. The process of turning sediment into rock is called lithification. It involves two main processes: compaction and cementation. Compaction occurs as the weight of overlying sediment squeezes out the water from deeper layers, pressing the particles closer together. Cementation occurs when minerals dissolved in groundwater precipitate out and fill the spaces between sediment particles, essentially gluing them together. Over millions of years, soft seafloor sediment becomes solid rock, preserving within it the record of the ancient sea that once existed above. Sometimes the sediments tell us about catastrophic events. A layer of disturbed, jumbled sediment might indicate a storm or tsunami that stirred up the seafloor. A layer containing fragments of volcanic ash tells us about an eruption, possibly thousands of miles away, that sent a plume of ash into the atmosphere, which then settled into the sea. A layer rich in clay minerals and poor in fossils might indicate a period of low oxygen when most life couldn't survive, an oceanic anoxic event that suffocated large portions of the ocean. Oil and natural gas, our primary fossil fuels, formed from organic matter that accumulated on ancient seabeds. During certain periods, particularly during the Cretaceous but also at other times, large amounts of organic material settled to the ocean floor without decomposing completely. This happened in low-oxygen environments, in enclosed or semi-enclosed basins where water circulation was restricted. The organic matter was buried under layers of sediment, and over millions of years, heat and pressure transformed it into oil and gas. When we drill for petroleum today, we're tapping into accumulations of ancient organic matter that once lived in ancient seas, capturing solar energy that fell on those waters hundreds of millions of years ago. The thickness of sediment layers also tells us about the passage of time. In some places, sediment accumulated quickly, perhaps several centimeters per thousand years. In these locations, a 100-meter thick sequence of rock might represent only a few million years. In other places, accumulation was much slower, with rates of perhaps a millimeter per thousand years. There, the same thickness of rock represents tens of millions of years. By measuring the thickness and determining how long it took to accumulate, geologists can reconstruct the rates of various processes in the ancient oceans. One fascinating aspect of ancient seabed sediments is that they record the Earth's magnetic field. As sediment particles settle through the water, any that contain magnetic minerals align themselves with the planet's magnetic field like tiny compass needles. When the sediment lithifies, this magnetic signature is locked in, creating a permanent record of the direction and strength of Earth's magnetic field at that time. Since Earth's magnetic field reverses periodically, flipping north and south every few 100,000 to a few million years, these magnetic reversals are recorded in the sediment as alternating bands of normal and reverse polarity. This has been crucial in understanding plate tectonics and in dating ancient rocks. The ancient seabeds also record sea level changes. When sea level was high, sediment accumulated in areas that are now dry land. When sea level dropped, these same areas were exposed and eroded. By mapping the extent of marine sediments and reconstructing where the ancient coastlines were, geologists can determine how sea level changed over time. This tells us about climate, about ice ages and greenhouse periods, about the configuration of continents and ocean basins. In all these ways, the sediments of ancient seabeds are like pages in a book, each layer a page, each sequence a chapter, the whole forming a complete history of Earth's oceans and the life they contained. Reading this book requires patience, skill, and interpretation, but the rewards are immense. A detailed understanding of how our planet has changed, how life has evolved, and how oceans and atmosphere and continents all interact in a complex, interconnected system. We often think of the ancient oceans in visual terms, imagining what they looked like, what creatures swam through them, what color the water was. But the ancient seas had a soundscape too, though it was probably very different from the cacophony of modern oceans. Let's close our eyes and listen to the ancient waters, trying to imagine what they might have sounded like. The first and most obvious difference is what would have been missing. The ancient oceans had no whales singing their haunting songs across thousands of miles. Whales didn't evolve until the Eocene, about 50 million years ago. Long after the age of marine reptiles had ended, there were no dolphins clicking and whistling to each other, no seals barking on rocks. All of these sounds, so characteristic of modern oceans, simply didn't exist during most of Earth's history. The mammals that would eventually return to the sea and fill these acoustic niches were still small, furry creatures living on land or hadn't evolved yet. But this doesn't mean the ancient seas were silent. Fish make sounds, usually low-frequency thumps or grunts produced by vibrating their swim bladders or grinding their teeth. These sounds might have filled the ancient waters, especially in areas where fish congregated in large schools. A reef teeming with life would have produced a constant background noise of fish communication, feeding, and territorial disputes. Crustaceans also make sounds. Snapping shrimp, which are common in modern tropical seas, produce loud clicks by rapidly closing a specialized claw, creating a cavitation bubble that collapses with a sharp sound. We don't know if ancient crustaceans had this ability, but it's possible. If they did, shallow tropical seas might have been filled with a constant crackling, like the sound of frying bacon, audible even above the water. The marine reptiles of the Mesozoic probably vocalized, at least to some extent. They had lungs and breathed air, so they could potentially produce sounds by forcing air past vocal structures, just as modern reptiles like crocodiles can bellow and hiss. A mosasaur surfacing to breathe might have exhaled forcefully, producing a sound like a whale's blow. Plesiosaurs might have called to each other, using sounds to maintain contact in murky water where vision was limited. But these sounds would have been rare compared to the constant vocalizations of modern whales and dolphins. The physical sounds of the ocean itself would have been familiar. Waves breaking on shores produced the same rhythmic crash and hiss that we hear today. The sound of rain falling on the water's surface would have been the same. Underwater, you would have heard the low rumble of waves passing overhead, a sound that penetrates deep into the water column. During storms, the sound would have been more intense, a chaotic mix of wave impacts, air bubbles being driven deep by breaking waves, and the rumble of thunder conducting through the water. Rivers entering the sea would have created distinctive sounds as fresh water mixed with salt water, carrying sediment and debris, creating plumes and eddies. In shallow areas, you might have heard the gentle grinding of sand and small rocks being moved by currents and waves. In coral reefs, the constant scraping and crunching of organisms feeding on the reef structure would have created a low background noise, occasionally punctuated by sharper sounds as rocks shifted or large pieces of coral broke off. Volcanic activity would have added to the soundscape in some areas and times. Underwater volcanic eruptions are extremely loud, producing low-frequency rumbles that can travel thousands of miles through the water. The sound of lava entering the sea, with the violent boiling and steam generation, would have been audible both underwater and above. During periods of intense volcanic activity, such as the Cretaceous when massive lava provinces were forming, these sounds might have been constant features of certain regions. One sound that definitely existed, though we rarely think about it, was the biological sound of creatures moving through the water. A large marine reptile swimming past would have created a sound, the water flowing over its body, disturbed by its fins or tail, creating turbulence. In schools of fish, the collective sound of thousands of bodies moving together would have been audible, a kind of rushing or swishing. The larger the animal, the more sound it would make simply by its movement. But compared to modern oceans, the ancient seas were probably quieter, at least in terms of biological sounds. The continuous chorus of whale songs that fills much of the modern ocean didn't exist. The clicks and buzzes of dolphins were absent. The vast, complex acoustic environment created by marine mammals simply wasn't there for most of ocean history. This silence, or relative silence, would have had implications for other creatures. Sound is an important sensory mode in water, which is too murky in many places for vision to work well. Without the acoustic clutter of marine mammal sounds, fish and other creatures might have relied even more on sound for navigation, communication, and finding prey. The deepest parts of the ancient oceans were probably nearly silent, far from the surface, far from any shores, far from any volcanic activity. The water would have been still and quiet. The only sounds would have been occasional faint rumbles from distant earthquakes or deep ocean currents, the very low-frequency sounds of large animals moving slowly through the abyss, and perhaps the faint patter of marine snow, organic particles settling toward the bottom. It would have been a place of profound peace, the kind of silence that humans rarely experience, a silence so deep it would be felt as much as heard. In the shallows, though, the ancient seas would have been livelier acoustically. The combination of wave sounds, fish noises, crustacean clicks, the movement of creatures, the settling of sediment, and occasional louder events like storms or volcanic activity would have created a varied soundscape. It might have lacked the richness of modern oceans with their whale songs, but it would not have been silent. It would have been an alien soundscape, different from anything we can hear today, but recognizable as the sound of a living ocean. If we could somehow visit these ancient seas, equipped with underwater microphones, what we recorded would be both familiar and strange. Familiar in its basic character, this is still water, still an ocean, still supporting life. But strange in its details, in the specific sounds made by creatures and processes that no longer exist. It would be a reminder that the ocean has not just a history visible in rocks and fossils, but an acoustic history as well. A history of sounds that were made once and will never be made again, lost in the deep time of Earth's past. And now, as we come to the end of our journey tonight, let's drift one more time through the memory of ancient seas. We've traveled together across hundreds of millions of years, from the first warm waters forming on a cooling Earth, through the Cambrian explosion of life, across the vast expanse of Panthalassa, into the tropical paradise of the Tethys, and through the bath-warm waters of the Cretaceous greenhouse. We've imagined glowing seas lit by bioluminescence, met creatures both familiar and bizarre, listened to the sounds and silence of waters long vanished, and explored the sediments that now preserve the memory of these ancient oceans. These seas are gone now, transformed by plate tectonics, evaporated in some cases, absorbed into the rocks in others. The creatures that swam through them are extinct, their lineages ended by the passage of time and the inevitable changes that Earth undergoes, but they left traces. The fossils embedded in sedimentary rocks tell their stories. The oil and gas we extract from underground formed from their bodies and the plankton they fed on. The limestone cliffs and chalk downs we see today were built from their shells. Even the salt in our blood echoes the composition of seawater, a reminder that we carry the ancient ocean within us, that we are descended from creatures that lived entirely in water and never left it. There's something profoundly peaceful about this connection to deep time. The ancient seas existed for so long, changed so slowly, maintained their basic character through cataclysms and extinctions and the endless cycle of evolution. They were patient, they were vast, they were persistent. And in their deep patience, in their vastness, in their persistence, there is something we can learn about letting go, about accepting change while recognizing continuity, about finding peace in the long view. The modern oceans are the descendants of these ancient seas. The Pacific Ocean occupies roughly the same basin as Panthalassa did, though everything else has changed. The water molecules flowing through modern seas have been part of the ocean cycle for billions of years, evaporating and falling as rain, flowing in rivers, accumulating in seas, rising and falling through deep currents. Some of the water you drink today might have been part of the Cambrian seas, might have passed through the body of a trilobite, might have lapped at the shores of Pangaea. There's no way to know, but the possibility connects us to that ancient time. Tonight, as you drift towards sleep, imagine yourself floating in warm, clear water under a cloudless sky. The sun is gentle, the water supports you effortlessly, and you have nothing to do but float, weightless, peaceful, safe. You're not in any particular ocean, any particular sea. You're in the eternal ocean, the one that has always been here in various forms, the one that will continue long after we're gone. You're connected to every creature that ever swam, every wave that ever broke, every tide that ever turned. The ancient seas teach us about time, not the frantic, hurried time of human life, but deep time, geological time, the kind of time where 1,000,000 years is a brief moment and 100 million years is merely a chapter. In this perspective, our worries and concerns become appropriately small. The things that seem so urgent, so important, so worthy of anxiety, are revealed as temporary, fleeting, as brief as a single wave in an ocean that has been rolling for billions of years. Let that realization be a comfort. You are part of something much larger and much older than yourself. The elements in your body were forged in stars that died before Earth formed. The water in your cells has been cycling through the planet for eons. The patterns of life you embody, breathing, eating, reproducing, moving, are patterns that go back to the earliest cells floating in the first oceans. You are not separate from Earth's history. You are part of it, a continuation of it, a current expression of processes that have been unfolding for 4 billion years. The ancient seas are still here, in a sense. They're in the rocks beneath your feet. They're in the fossils in museum collections. They're in the chemical composition of seawater. They're in the DNA of every living thing, which preserves the memory of evolution going back to those first cells in those first warm waters. They're in the stories we tell about Earth's history, in the science that reconstructs the past, in the imagination that tries to picture what it was like. As you settle into sleep tonight, let your breathing become like gentle waves on a shore, slow, regular, rhythmic, in and out, like the tide, rising and falling, like the swells in the open ocean. Each breath connects you to the atmosphere, to the oxygen produced by photosynthetic organisms billions of years ago, and continuing to this day. Each breath is part of a cycle that has continued unbroken since life began in the ancient seas. Your body is mostly water. You are a small, temporary ocean carrying a bit of the ancient sea within you. The salt in your blood, the water in your cells, the minerals in your bones, all came ultimately from the ocean. You are made of the same materials that filled the Cambrian seas, that swirled in Panthalassa, that lapped at the shores of lost continents. And when you return to the earth, as all things must eventually, those materials will cycle onward, perhaps eventually returning to the sea, completing a circle that has no beginning and no end. Let this be your last thought before sleep takes you. You are safe. You are part of something vast and ancient. You are connected to the deepest history of Earth. And in the morning when you wake, the ocean will still be there, rolling and turning and carrying on as it has for 4 billion years. The tides will ebb and flow. The currents will circulate. The waves will break and reform, and all of it will continue, patient and persistent. The way it always has, the way it always will. Rest now. The ancient seas have done their work. They've brought you to this moment, this quiet space between waking and sleeping, this peaceful drifting toward dreams. Let them carry you the rest of the way. Let yourself sink gently into sleep, into rest, into the deep, dark, warm embrace of waters that remember everything and ask nothing in return. Good night, sleep well, and may your dreams be as vast and peaceful as the ancient seas that once covered Earth, as timeless as the ocean that has always been here, as gentle as the waves that have been rolling since the beginning of the world. The ancient seas are calling you home. It's time to rest.